Hey everybody, welcome back to your favorite subject in the whole world, biochemistry. For those of you who don't know me, my name is Alfonso Flores and I'm one of your many biochemistry tutors here at the University of Texas at Dallas. So as you'll see here for Dr. Marsh's and Dr. Taylor's sections, next Tuesday you'll be covering enzyme kinetics. So it's something that you haven't covered yet, but I wanted to go over it now so that when next week comes by, you hit the ground running and this is super easy for you. Okay, so I broke down enzyme kinetics into two parts, and that is enzyme classifications and enzyme kinetics by itself. So let's start off with what exactly an enzyme is. So what is an enzyme? An enzyme is made up of amino acids, so it is a polypeptide. Or you can have more than one polypeptide chain made up of amino acids. So it's a polypeptide, or plural polypeptides, made up of amino acids which catalyze reactions. And this right here means reactions. So it is a polypeptide made up of amino acids which catalyze reactions. So let's pretend that we have a polypeptide chain and it starts off with M and then A, G. So M for methionine, A for alanine, G for glycine, and it goes on and on and on until we have another methionine, asparagine, glutamine, and serine. So let's say this is the sequence of our enzyme. So this is enzyme A. So an enzyme is a polypeptide, so that's what we have here, made up of amino acids, which is what each of these single letter abbreviations represent. And what they do, what enzymes do, is they catalyze reactions. So over here, I'm going to draw what that looks like. So let's pretend that this polypeptide chain, when you draw it out in its chain form, it looks like this. It's a big enzyme, just like that. And we're going to call this enzyme A. Okay. So enzyme A catalyzes reactions. So here we have our substrate. It's this red dot right there. And so what this enzyme does with a substrate, so let's call this substrate A. So what this enzyme does with the substrate, there should be an R there, it forms an enzyme substrate complex. And so as you can see here, the enzyme has now bound the substrate. And don't get too worried about these words like substrate. All that means is molecule. So you can just replace the word substrate with molecule if that'll help you out a little more. So enzymes are made up of polypeptides and they bind substrates, forming the enzyme substrate complex. Enzyme substrate complex. And what happens next is the enzyme, once it's catalyzed a reaction, it releases this substrate, but it releases it as a product. So this is the product. It's this blue box. And don't worry if this is too general for now. We're going to do a lot of examples later on in this video, which will clear things up. So let's start from the beginning. An enzyme is a polypeptide made up of amino acids which catalyze reactions. Okay, and what that means is that they make reactions like this, turning substrate A into product A. they turn substrate A into product A super fast. Okay, so that's all enzymes do. They take substrates, form enzyme-substrate complex, and they turn that substrate into a product. And so we can represent this whole diagram with a very general equation, but it's an equation that you should know and that you should know for the rest of your life. And that is enzyme plus substrate forms the enzyme substrate complex, and then enzyme substrate complex forms enzyme plus product. This equation right here, I want you to burn it into your brain. I want you to write this equation every single day until your next exam, or until your MCAT or DAT. Well, no, you won't see this on the DAT, but for sure the PCAT. Okay, so enzyme plus substrate forms the enzyme substrate complex, and then we go from the enzyme substrate complex to enzyme plus product. Don't worry about the reverse reaction here, because it's hardly ever seen in nature, so we just ignore it. Okay, so we know what an enzyme is now, for the most part, and we know what enzymes do. They catalyze reactions, they make reactions occur really fast, and as you can see here, substrate A was turned into product A. Okay. So all this that we've gone through so far, you should really do your best to remember this, because this is going to help you for the rest of the class. Okay, so I broke up enzyme kinetics into two things: enzyme classifications and enzyme kinetics. So even though we know what enzymes do, and that is they catalyze reactions, even though we know what they do, we still have to classify enzymes, because not all enzymes catalyze the same types of reactions. So don't worry if you don't really understand what that means yet. We're going to go through plenty of examples. Okay, so this is a protein. It's more specifically, it is an enzyme, and the reason, or the way we know that, is because it has a binding site, that's this blue part right here, and it has a catalytic site. So if a protein has a catalytic site and a binding site, that pretty much means that it catalyzes a reaction, just like what we saw over here. Enzyme binds substrate, form enzyme substrate complex, and it forms a product. And you see this molecule right here, the black one, that is the substrate. And the next step would be releasing the enzyme and also releasing the substrate, but now it has been turned into a product. Okay? And enzymes have binding sites and they have catalytic sites. And so you're really going to want to know the difference between the binding site and the catalytic site. So we'll go over that right now. The binding site recognizes the substrate. So binding site recognizes the substrate. And what does the catalytic site do? It reduces the activation energy necessary to turn this substrate into this product. Okay. So the binding site recognizes the substrate, and the catalytic site reduces the activation energy, which turns this substrate into this product. This is really important. The catalytic site reduces the chemical activation energy, okay? Not the Gibbs free energy. And don't worry, we'll go over that at a later date. Okay, so enzymes. This is an example of an enzyme, urease, right here. And as you can see, urease binds with urea, which is this molecule right here. It binds with urea, so enzyme plus urea Okay. And what it does is it turns urea into CO2 and ammonia, and at the very end it releases the enzyme. And if you'll see here, urease requires water. So this urease right here requires water, but not all enzymes require water, which is what makes urease a hydrolytic enzyme, which uses water to cleave urea into carbon dioxide and ammonia. So another way that we can write this is urease plus urea forms the urease urea complex, and then urease catalyzes a reaction which turns urea into carbon dioxide and ammonia. Okay. And this is analogous to enzyme plus substrate forming the enzyme substrate complex, and then enzyme plus product. So like I said, this equation is very important and you should remember it. Okay. So why do we need enzymes? Well, the reason why we need enzymes is because this reaction right here, so this reaction, here's what you have to know. This reaction occurs naturally in nature. I guess that's what naturally is. It occurs naturally, but if we include an enzyme, then this reaction will happen a lot faster. And we can look at this slide over here on the left-hand side. So the catalyzed rate is essentially 30,000. So it's 30,000 units per second. So every second, 30,000 of these urea are able to be turned into CO2 and NH3. But if we don't use an enzyme, then one is turned over every, 3 to the 10th, or 3 times 10 to the 10th. That is 30. Yeah, there you go. Wait, is that right? Yes, okay. That's one every 30 billion? Yeah, every 30 billion seconds. So as you can see, with a catalyst, with an enzyme, this reaction happens a lot faster. And that's pretty much what this slide means, or what this slide is trying to say. That with enzymes, these reactions, even though they're slow, without the enzyme, with an enzyme, it'll occur a lot faster. So I hope that helps. Okay, enzymes endow cells with the remarkable capacity to exert kinetic control over thermodynamic potentiality. All right, so as I was saying over here, there are many different types of enzymes, and urease is an example of an enzyme which requires water to perform its reaction. But not all enzymes require water. And this is what makes urease a hydrolytic enzyme. And so now we will talk about enzyme classifications. So the enzyme classifications are as follows. So the very first enzyme classification, so enzyme classifications. So the very first one is oxidoreductases. The second one is transferases. The third one is hydrolases. The fourth one is OTHL. So the fourth one is hydrolases. So that's, let me check. They're liases. No, that's the same thing. Okay. So the fourth one is liases. The fifth one is isomerases. Sixth is that is ligases. And there's a seventh one, which is translocases. All right, so let's back up just a little bit. We were talking about urea, which is an enzyme that uses water to cleave. Sorry, we were talking about urease, which is an enzyme that uses water to cleave urea into CO2 and NH3. Okay? So because urease uses water to cleave, that's the key word, cleave urea, because of that, it is a hydrolase. Okay, so that's a number 3. So the enzyme classification number is 3 for hydrolases. And that is something that you're going to want to know for your exam. If they ask you which major enzyme classification is number 1, that would be your oxidoreductases. If they ask you what is the enzyme classification number of liases, then you'll say it is number 4. Okay, so you're going to want to know oxidoreductases, which enzyme classification they are, and you're going to want to know what these types of enzymes do. You're going to want to know for every single one of these. So we covered hydrolases, and we know that hydrolases use water to cleave urea into CO2 and ammonia. Sorry, not all hydrolases, only urease does that. Urease gets urea, uses water, cleaves it into CO2 and NH3. Okay, and let's see. Okay, so over here on the left-hand side, you'll see EC number 1, that is oxidoreductases, EC number 2, that is transferases, EC number 3, that's hydrolases, EC number 4, that's liases. So I think earlier I said that hydrolases and liases were the same thing. I was wrong, I misspoke. Number 5, it's isomerases, and number 6, it's ligases, and there's a new one, translocases. So these are just the major enzyme classifications. Okay, so we're going back to urease. If we look up urease on Wikipedia, we'll see that it has an EC number of 3.515, okay? Now, this, the whole number, for us, for now, it doesn't matter. All we care about is this part right here, EC3. EC3 corresponds to hydrolases, which is exactly what urease is. And let's see if we can confirm that somewhere. Yeah, these enzymes catalyze the hydrolysis of urea into carbon dioxide and ammonia. So yeah, if they cleave using water, then they are hydrolases. All right, and so these are examples of each enzyme class. So the enzyme class 1 are the oxidoreductases. And if you'll see here, this CH3, CH2OH, that it looks, let's see, that looks like this. No, that's a little, Too many carbons. So that's ethanol right there. And this ethanol gets turned into acetaldehyde. So what happened to this carbon right here? Well, if you look at the picture over here on the right-hand side, you'll see that this carbon was actually oxidized. And if a carbon is oxidized, or if anything is oxidized or reduced, then the type of enzyme that catalyzes this reaction is an oxidoreductase. Oh, something that I should have mentioned in the very beginning is that anytime you see the suffix ase, that means that it is an enzyme. So anything that ends with ase, that's an enzyme. Okay, so here we have an alcohol, and it gets turned into acetaldehyde. So it was oxidized, therefore an oxidoreductase catalyzes this reaction, which is an oxidoreductase over here. But more specifically, the oxidoreductase that catalyzes this reaction is alcohol dehydrogenase. So alcohol dehydrogenase, remember, ACE stands for enzyme. Alcohol dehydrogenase is an oxidoreductase, okay? The major enzyme classification of alcohol dehydrogenase is oxidoreductase. And for your exam, they most likely will give you a chemical reaction, and you'll have to tell which one or what type of enzyme classification, or what is the enzyme classification of the enzyme that catalyzes this reaction. So you're going to want to become very fluent with looking at chemical reactions and seeing just what happened in them. Okay, so let's go with transferases. Transferases, what they do is they take something from one molecule and they give it to another. So as you'll see here, ATP binds with the enzyme, and it transfers a phosphate, a PO4 3-. It transfers one phosphate from ATP to glucose, turning glucose into glucose 6-phosphate. So a transferase, more specifically glucokinase, takes one phosphate from ATP. So ATP stands for adenosine triphosphate. It gives one of those phosphates from this triphosphate to glucose, turning glucose into glucose 6-phosphate, and turning ATP into ADP. All right, so a transferase transfers something from one molecule and gives it to another. And it's almost always a functional group. So this is the structure of ATP, just the phosphates. And no, you don't have to know the structure, but it does help. We don't care about that. Okay, so this right here is ATP, and what a transferase is going to do, more specifically glucokinase, it's going to cleave off this phosphate right here, this PO4 3-, and it's going to give it to glucose, forming glucose 6-phosphate. So that's what a transferase does. Okay, so we are going to move forward, and we're going to try to answer some of these questions. well, before that, let's just look at hydrolases. So here we have a peptide, a polypeptide, and as you'll see here, there's water, and water is introduced and it creates a shortened polypeptide and a C-terminal residue. Pretty much what this tells you is that water was used to cleave right here, and we were able to turn this part into the shortened polypeptide and this part right here into the C-terminal residue. So this would be a cleavage using water, so therefore it is a hydrolase. And more specifically, this reaction is catalyzed by carboxypeptidase A. All right, and then we also have lyases, and these cleave using pretty much anything but water. So lyases, they cleave just like hydrolases. So they cleave, well, they also form bonds. They cleave using anything but water. It's like they're allergic to it. Okay, so that's lyases. They cleave or they form bonds, and they do this using anything but water. So you ever see a cleavage reaction, as you'll see here? You see how this acetaldehyde has this part right there, but it's missing this CO2, which is right there. That's how you know a cleavage was done, and there's no water here, so therefore it is not a hydrolase. And then isomerases, all they do is they rearrange molecules. So if you'll see here, you see how there's these two CO2 groups on the same side? Well, this enzyme, malleate isomerase, takes this molecule and it puts them on opposite sides. So that is an isomerase. So the chemical formula for isomerases is the same, but it's just the structure that's different. And then we also have ligases, which put together molecules. So look at this pyruvate and this CO2 right here. This enzyme, pyruvate carboxylase, which is a ligase, it's going to put pyruvate and CO2 together, forming oxaloacetate. And this CO2 is this CO2 right there. And it does it using ATP. All right, I think this is good enough for now. So let's begin. So here are the enzyme classifications, and this is a little mnemonic that someone made, someone way smarter than me, and it is OFF-LIL-T. So O stands for oxidoreductases, and that's 1. T stands for transferases, which is 2. H stands for hydrolases, 3. L stands for lyases, which is 4. I stands for isomerases, 5. And the last L stands for ligases, 6. And that is 7. And also these are the helpful equations that we will be using throughout this whole review session. You may want to write these down. They're going to be very helpful later. All right, let's start with the first question. A certain glycolytic enzyme catalyzes the conversion of D-glucopyranose 6-phosphate to D-fructofuranose 6-phosphate. Recent evidence supports the role of a cysteine-diol intermediate in catalysis. What is the major classification of the enzyme which catalyzes this reaction? So here's the question. What is the major classification of the enzyme which catalyzes this reaction? All right, so this right here is G6P. And this right here is F6P, right, from the question. So G6P and F6P. And if you'll actually count the molecular formula, or if you write out the molecular formula, you'll find out that they have the same molecular formula. So they have the same molecular formula. The only thing that changed is the structure. So what do you think is the enzyme classification of the enzyme which catalyzes this reaction? So in other words, if we have this enzyme and it reacts with G6P and it forms the enzyme G6P complex, so it forms a complex, and then it releases this substrate as a product, and the product is now F6P. If we have this enzyme, what is the enzyme classification? The major classification. Well, since the molecular formula stayed the same, which is something that you can verify by counting all the carbons, hydrogens, oxygens, and phosphorus, you'll see that they have the same molecular formula, which means that the only thing that changed is the structure, and therefore this is an isomerase. So isomerases, they rearrange molecules, which is exactly what has happened here. Okay, for number 2, hexokinase is an enzyme found in muscle cells. What is the major classification of these enzymes? Okay, so hexokinase is an enzyme found in muscle cells. So what do you see happening here? You have glucose, and the product is glucose 6-phosphate. And you also have ATP as one of the substrates, and it gets turned into ADP. So ATP was turned into ADP, and one of those phosphates from adenosine triphosphate, so ATP stands for adenosine triphosphate, One of those phosphates is being donated to this molecule. So if a molecule transfers, that's the hint, if the molecule transfers something from one group to another, what type of enzyme is that? Or what is the major classification? That is going to be a transferase. My voice keeps cracking. Yeah, transferase. All right, now some of you may ask, Alfonso, why isn't it why isn't it hexokinase? Well, the reason for that is because hexokinase is not a major classification, right? The questions are asking for the major classification. Let's see if we can find hexokinase as part of the transferases. Well, we have glucokinase. Yeah, anytime you see kinase, it's a transferase. But let's see if we can find it over here. No, we can't. But yeah, anytime you are transferring one group to another, that is a transferase. All right, so number 3, what is the major classification of the enzyme which catalyzes the following reaction? So look at alanine over here and look at oxoglutarate. What is happening to alanine and what is happening to oxoglutarate? So pause the video and look at the substrates and look at the product, and I want you to, I was going to say I want you to tell me, but I want you to ask yourself, student, what is happening to alanine or oxoglutarate? Yeah, so go ahead and pause the video. All right, for those of you who paused it or just decided to watch through, I commend you. If you'll see here, alanine, once alanine is turned into pyruvate, it loses this NH3 plus, and it is replaced with a C double bond O. And this oxoglutarate, look at this carbonyl right here. This carbonyl gained an NH3 plus. Interesting. So it's almost as if a certain enzyme took this NH3 plus and it gave it to oxoglutarate. So an enzyme took this NH3 plus, gave it to the oxoglutarate, which turned the oxoglutarate into glutamate. So if you see that there was a transfer of functional groups. So alanine got turned into pyruvate, oxoglutarate got turned into glutamate, and the way that happened was by an enzyme taking this NH3 plus, giving it to oxoglutarate, turning oxoglutarate into glutamate. So whenever functional groups are transferred from one to another, what is the major classification of the enzyme? It is transferase. So remember, for transferases, a functional group is transferred from one molecule to another. So just like it happened here with ATP, where one of the phosphates was given to alpha-D-glucose, the same thing happened here. The ammonia from alanine was transferred from alanine to oxoglutarate, and by doing that, oxoglutarate was transferred or was converted into glutamate, and subsequently alanine was turned into pyruvate. So for that reason, the answer for number 3 is B. All right, number 4. Pyruvate decarboxylase is an important enzyme necessary for the production of acetyl-CoA. What are the respective major enzyme classifications? Okay, look, major enzyme classifications. So what are the major enzyme classifications for the reactions catalyzed by pyruvate decarboxylase and alcohol dehydrogenase? So here's pyruvate decarboxylase, and here's pyruvate over here. So if you'll see here, pyruvate lost CO2. So pyruvate was cleaved, and it doesn't look like any water was used here. So anytime you have a cleavage that does not require water, what type of reaction, or what is the major classification of the enzyme that does that? That would be a lyase. And so pyruvate is turned into acetaldehyde, so it loses this CO2, and the cleavage happens without water, so therefore it's a lyase. And then you have acetaldehyde getting turned into ethanol. So what is happening to acetaldehyde as it gets turned into ethanol? Well, this carbon right here was actually reduced. So it used to have 2 bonds to oxygen, now it only has 1 bond to oxygen, so you can see that it was reduced. And what type of enzymes catalyze oxidation reduction reactions? That would be oxidoreductases. So for that reason, the answer to number 4 is lyase and oxidoreductases. Some of you may ask, why isn't it B? Well, we're not using water, or pyruvate decarboxylase doesn't use water to cleave, so therefore it's not a hydrolase. Why isn't it E? Well, pyruvate decarboxylase is a lyase, but alcohol dehydrogenase, the major enzyme classification, is an oxidoreductase, not a dehydrogenase. This right here is not a major it's not a major enzyme classification. All right, so you're going to want to get comfortable with looking at chemical reactions and deciding what is the EC number or the major classification of each of the enzyme that catalyzes a reaction. So for this one, G6P into F6P, what would be the EC number for it? So if we take off lil T, we know that isomerases are 5, so therefore the EC number is 5. For number 2, off lil T is number 2, so therefore the EC number would be 2. Number 3, this is a transferase, the one that catalyzes this reaction, so therefore the EC number is also 2. And number 4, the major enzyme classifications for these two enzymes, EC numbers, it's going to be lyase, so that would be off lil T, so this will be the L for lyases, that's 4, and oxidoreductases, that's 1. You're going to want to get comfortable with EC numbers and their major enzyme classifications. So by now you're probably wondering, what are Michaelis-Menten enzymes, or what are Michaelis-Menten kinetics? And these are kinetics which are displayed by enzymes which have one catalytic subunit. Okay, so this is an enzyme right here, and this enzyme has one catalytic subunit. Now this may seem a little simple, but this is extremely important, and it's what makes the difference between Michaelis-Menten enzymes and allosterically controlled enzymes. So this right here is going to be a Michaelis-Menten enzyme. And then you're also going to have allosteric enzymes. Allosteric enzymes. And what that means is that they have more than one catalytic subunit. So that would look something like this. Okay, so look at this enzyme right here, the one on the right. You see how it has two of these little indentations? We're going to call this the catalytic site. Catalytic site. Well, look, this one right here, the Michaelis-Menten enzyme has one catalytic site, but the allosteric one has 2 catalytic sites. So this means that allosteric enzymes have more than one catalytic subunit. All right. That's a very big differentiation between Michaelis-Menten enzymes and allosteric enzymes. Yeah, so allosteric enzymes have more than one catalytic subunit. Michaelis-Menten enzymes, only one catalytic subunit, but they can have more than one active site. All right, so this means that the enzyme could have an active site here and an active site there. What the active sites do is they catalyze the reaction. That's very important for you to know, and we actually went over that at the very beginning of the video. So if that doesn't make sense, just go ahead and go back to the beginning of the video where I showed the enzyme with the binding site and the catalytic site. So I'm going to say that this right here is the binding site, and that this right here, the red portions, are the catalytic sites. And the binding site and the catalytic site are very important. Binding site. So the binding site is the site of the enzyme which actually recognizes the molecule, and the catalytic site is the active site, which is this part right here. The active site. That's the site that actually catalyzes the reaction. So the whole catalytic site is composed of two things: the binding site and the active site. Never forget that. That's very important. So Michaelis-Menten enzymes, one catalytic subunit. Allosteric enzymes, more than one catalytic subunit. And the Michaelis-Menten enzymes, that's exam 2 material, whereas allosteric enzymes, that is exam 3. All right, so let's see. So Michaelis-Menten enzymes, because they have one catalytic subunit, they produce graphs that look like that. That's perfect. So they produce graphs that look like that. They have a rectangular hyperbola. Remember those two words, rectangular hyperbola. So they have a rectangular hyperbola for a graph, and the x-axis is your substrate concentration, and your y-axis, that is your initial velocity. And so what's happening here is that you have an enzyme with a substrate, and they are forming an enzyme substrate complex. And once they form that enzyme substrate complex, they will form enzyme plus product. All right. Okay, so what you have here is an enzyme with a substrate forming the enzyme substrate complex, and then enzyme plus product. All right, so this product right here, it doesn't matter what it is. This is what we are measuring with this graph. As the enzyme is getting substrate and forming product and doing that cycle over and over and over again, so every time it forms product, it goes back to bind with substrate. As soon as it forms product, that's what we're measuring. And as we add more substrate, so look at this. We're going to say this right here is 5 millimolar. So this is substrate concentration in millimolar. So at 5 millimolar, this right here is the velocity of the reaction. What this is measuring is the amount of product that's forming per unit of time. So the enzyme grabs a substrate, forms the enzyme substrate complex, and then you have enzyme plus product. The enzyme goes back to react with more substrate. And that's what we're measuring. So velocity is concentration of product per unit of time. And substrate concentration is the amount of substrate, the amount of molecule that the enzyme is acting on. All right, so Michaelis-Menten enzymes make these types of graphs, rectangular hyperbolas. And something that I want you to pay attention to is this substrate concentration over here. Let's say that this is 7 millimolar. Look at this. At 7 millimolar, this is the velocity right here. Notice how that velocity and the one at 5 millimolar substrate, it's not much different, right? They're very close to one another in terms of velocity, right? So there's like a little scale, a little measuring. Well, what if we made the substrate concentration 10 millimolar? This would be the velocity now. And that difference right there between the 10 and the 7, that's even smaller. So as you can see, as we increase the amount of substrate, we are saturating the enzymes with substrate, which is forcing us to reach this value right here called Vmax. Vmax is at the very top of the hyperbola. What's happening is we have a beaker, and this beaker is full of enzymes. So these circles are going to represent enzymes. All right, so these circles, or these green circles right here, represent enzymes, and what we're going to do is we're going to start adding just a little bit of substrate. So we're going to sprinkle in, here, let me draw this. I'm an artist. Not really. So we're going to call this little mountain of red dust, we're going to call this our substrate, okay? So this right here is our substrate. And as you can see, it is in a solid form. And what we're going to do is we're going to take this substrate and just put a little bit into the beaker. So let's say we put in 1 millimolar of substrate. So this right here represents 1 millimolar, those dots right there. It's a very small amount of substrate. It's very tiny. So we're going to put the 1 millimolar here. So when we put 1 millimolar of this substrate, look at the velocity of the reaction. Well, what happens when we put in 2 millimolar? So now we put in 2 millimolar. What's going to happen to the velocity as we put in 2 millimolar? So this is 2 millimolar. The velocity increases, and so now it's at this level. Before it was here, and now it is there. And what's going to happen when we put, let's say, 4 millimolar? The velocity is again going to increase. And now it's that velocity. And so what's happening is we're putting in more substrate, and the enzymes are reacting with the substrate and forming more and more product. But eventually, look at this, we can add so much substrate to the point where the amount of substrate is way more than the enzymes. So all of the enzymes are working constantly. They're pumping out product as fast as possible. And that right there is what generates this Vmax. It's when all of the enzymes are saturated. remember the word saturated. If the enzymes are saturated, they are working at Vmax. Enzyme saturated, Vmax. It's easy to remember. Okay, there's something really important that you should be getting from a Michaelis-Menten graph, and that is your Km value. Don't worry if you don't know what a Km value is, I'll explain that in just a little bit. But if you ever see a Michaelis-Menten graph, there's two things that you should look at. The first thing is Vmax, and then the second thing is half of the Vmax. This is crucial, all right? Whenever you're given a Michaelis-Menten graph, I need you to look at the Vmax first, and then I need you to look at 1/2 of the Vmax. So we're going to do that just now. So here's our Vmax right there. And now 1/2 of the Vmax, if I'm not mistaken, is right there. You guys be the judge and tell me whether or not that looks like 1/2 of the Vmax. I think it looks perfect. So that right there is 1/2 of the Vmax. The reason why I want you to look at the 1/2 of the Vmax is because that initial velocity, the 1/2 of the Vmax, tells you what your Km value is. Km stands for Michaelis-Menten constant. So from this point right here, the 1/2 of the Vmax, I want you to make a line to the hyperbola as straight as you can. And then as soon as you strike the hyperbola, I want you to go down. All right, this value right here, this value of substrate concentration is your Km. So whatever this value is right here, that is your Km. And we're going to say that Km is 1.5 millimolar. All right. So now that we have found our Km, we can talk a little bit more about it. But before I go on, let me see if there's something that I may have missed. No, I think everything looks good. Okay, so before we move on, I want to reiterate, whenever you're given a Michaelis-Menten graph, I want you to look at the Vmax, then I want you to look at half of the Vmax. So let's say the Vmax was 200 millimolar per second. Then I want you to half that number, so 100, which would be right here, and then draw a line through the graph until you strike the hyperbola, and then go down, and this value right here is your Km. Now let's talk a little bit more about your Km. Km stands for Michaelis-Menten. That's not how you spell Menten. The biochemistry gods are mad at me for misspelling their names. Michaelis-Menten constant. All right. Km is a concentration. So look, you got the units, millimolar, which is a concentration. Km is the concentration of substrate. This is crucial. I need you to write this down. Km is the substrate concentration at which your initial velocity is equal to the 1/2 Vmax. This little statement right here, this little nugget of wisdom, is one of the most important concepts of this whole unit. Km is the substrate concentration at which your initial velocity is 1/2 of the Vmax. And let's find our Km. We know that the Km is this value right here. So when the substrate concentration is 1.5 millimolar, so don't even think about Km right now. Just look at this number right here. We know that this is 1.5. When the substrate concentration, right, because that's the x-axis, when the substrate concentration is 1.5 millimolar, what is our initial velocity? 1/2 of the Vmax. It just so happens that at this substrate concentration, that is also our Km value. All right, we're going to see some more graphs, so don't worry if you don't understand that at this moment. I think that if you see a little more examples, you'll get the idea of what I'm talking about. Okay, so that's Michaelis-Menten kinetics, and this right here is the allosteric enzyme, the one that I was talking about earlier. But yeah, it's exam 3 stuff. Let's not worry about that right now. The time will come. Oh, okay. So enzyme kinetics, Michaelis-Menten enzymes. The general formula is enzyme plus substrate forms what? The enzyme substrate complex, and then this forms enzyme plus product. So this first step right here, enzyme plus substrate forming the enzyme substrate complex, that is governed by the rate constant K1. So the forward reaction of E plus S forming the enzyme substrate complex, that is governed by the rate constant K1. So therefore, the reverse reaction is K sub -1. And going from the ES complex, the enzyme substrate complex, to the enzyme plus product, that is governed by the rate constant K2. Just so you guys know, K2, a lot of times they'll call it Kcat, and they are essentially the same thing. I say essentially because there are some stipulations when these two things aren't equal, but I've never seen an example where they're not equal, so I don't know what to tell you. Okay, for the most part, K2 is equal to Kcat. There's some situations where this is not true. I've never seen a situation, and I've never heard of a single situation where this wasn't true. So take that as you will. Okay, so this K2, it is the catalytic rate. That's where the Kcat comes from. It is the catalytic rate constant. It is the speed at which an enzyme catalyzes a reaction. So here you have enzyme plus substrate forming enzyme substrate complex. Going from this complex to the enzyme plus product, it's governed by K2. If K2 is small, do you think that we're going to form a lot of product? And the answer is no, we're not. If K2 is small, then that means that the rate at which the enzyme substrate complex forms product is very low. And this is going to be very important as we go on through the unit. So for this part right here, the Michaelis-Menten enzyme kinetics, let's just draw another graph. That's a Michaelis-Menten graph. The top part is called what? This upper limit, what do you call it? That is correct. Vmax. You guys are so smart. Okay, and what are the units? What are the units of Michaelis-Menten enzyme kinetics? For the x-axis, that'll be substrate concentration, which is a concentration. It could be millimolar, it could be micromolar. For this one, we'll make it micromolar. So for those of you who don't know, I don't know if it's a Greek letter, but I know it's called mu. All right, so we'll just go with that. So the x-axis, it's going to be in micromolar, it's a concentration, and the y-axis, that's velocity, which is measured in products per unit of time. So that's initial velocity. All right, so we're going to go through some things that we didn't cover in the other graph. So what you should know is that at low substrate concentrations, the graph follows first order kinetics. So at low substrate concentrations, the graph follows first order kinetics. And what that means is that as you start increasing the amount of substrate, the velocity also increases. Do you agree? Yes. So what first order kinetics means is that as you increase the amount of substrate, you also increase the velocity. And you can see that right here. I'm going to give these some arbitrary values just to illustrate that point. So I'm going to call this 5 micromolar. We'll call this 10 micromolar. And I'm going to call this 1000 micromolar. So 1 micromolar is right here. Okay, so look at this. When I'm at 1 micromolar, this is my velocity. When I'm at 2 micromolar, what happened to my velocity? Did it increase? Yes, it increased. So that's first order kinetics. As you increase the substrate concentration, so does the velocity increase. But what happens when I'm at, let's say I'm at 10 micromolar? What happens to the velocity? It goes to Vmax. Now, what if I increase that concentration by 100 times? What happens to my velocity? It stays the same. I'm still at Vmax. What if I put in 5,000 micromolar of substrate? Would you expect the velocity to increase? The answer is no. It should stay at Vmax. And the reason for that is because if you look at this picture right here, this one, all of the enzymes are completely saturated with substrate. It doesn't matter how many more molecules of substrate you add, because you still have the same amount of enzymes. That's the most important part here. You have the same amount of enzymes, so it doesn't matter how many substrates you add, how much molecule, or what if you increase the concentration. It doesn't matter. They're still going to be working at the exact same rate of K2. But how could you increase the Vmax? Well, the way that you could do that is by increasing the amount of enzymes. If you increase the amount of enzymes, you will in fact increase the velocity. So this right here would be the new Vmax. Okay, so I went off on a tangent. What I was trying to get at over here was that as you increase the amount of substrate concentration, it doesn't matter. It follows zero order kinetics. That's what I was trying to say. Zero order kinetics. And the reason why increasing the amount of substrate doesn't matter is because it's not increasing the velocity. So that's zero order kinetics. But you could increase the Vmax if you increase the amount of enzyme. And so we can see that in this very important equation that goes Vmax is equal to K2, which is how fast an enzyme works, So Vmax is equal to K2 times the amount of enzyme, so the concentration of enzyme, times the number of active sites. Number of active sites. So notice how to increase Vmax, this equation right here does not include substrate concentration. Sure, if you increase the amount of substrate concentration, you'll increase that initial velocity, but eventually you'll reach this upper limit no matter how much substrate you add. No matter how much substrate you add, you won't increase that upper limit. But if you want to increase Vmax, increase the amount of enzyme, and boom, you got it. So I hope that makes sense. How do you find Km? So just how we described in the previous graph, all you got to do is find your Vmax. So boom, that's my Vmax right there. What's half of it? I'd say that's right here. And then just draw a straight line as straight as you can, and then boom. I'm saying boom too many times. I gotta stop. Alright, so this right here, that is our Km value. And remember, Km is the concentration of substrate at which your initial velocity will be 1/2 of the Vmax. Km is also something else. It's a measure of affinity. And the way that you calculate that affinity is using this equation. Km is equal to K sub minus 1 plus K2 over K1. So essentially this equation right here, look at K sub minus 1 and look at K2. These top values are these values over here. K sub minus 1 and K2 are the dissociation of the enzyme substrate complex over the association, over the formation. So the bottom part is the formation of the enzyme substrate complex, whereas the top part is the dissociation of the enzyme substrate complex. That's very important for you to know. So that is Km right there. So Km can either be given to you or you could be forced to calculate it on your own. But you should have already got some experience on calculating Km, since most of you have been doing your problem sets, right? I hope so. Okay, so this is an important equation right here, and that's an important equation, and well, they're all right here. Okay. Okay, so this right here is a Michaelis-Menten graph, but I just haven't drawn that straight line or that rectangular hyperbola that you're used to. And that's because this graph right here is an actual graph from a real experiment that was conducted. And as you guys know, in real life, the numbers aren't that pretty. Just like in, I was gonna say math, but you guys know what I'm trying to say. So look at this Michaelis-Menten graph right here on the right. It generates a rectangular hyperbola for the most part. I mean, you see how this part of the line is a little below, and right here it's a little above. For the most part, it follows that rectangular hyperbola, so it is a Michaelis-Menten graph. And if you look right here at the bottom, where I have the data, look at the substrate concentration that we started off with. 0.04 millimolar. So this is equivalent to millimolar because that's millimoles per liter. So at this substrate concentration of 0.04 millimolar, look at the velocity. It is whatever it says there, 0.7, yeah, 0.07. 0.07 millimolars per liter of product per unit of time. So, so this right here should actually say millimole per liter per time. And so should this. Whoa, stop working. Oh, there, we're back. Okay, so look at the velocity at this substrate concentration. It is 0.07 millimolar per liter per unit of time, and as you increase it, let's say to 0.7 all the way over here, look at the velocity. It is about 0.2, yeah, 0.2 millimolar per liter per unit of time. Per unit of time. So whenever you look at these graphs, what's the first thing that you guys should look at? That is the Vmax. And then the second thing you should look at is the 1/2 of the Vmax. So there's 0.200. So what is 1/2 of that? 0.1, right? So this right here is 1/2 the Vmax. And if we make a straight line going here and then down, this right here, this substrate concentration is your Km value. So this is your Km. And your Km is equal to the substrate concentration at which your initial velocity is 1/2 of the Vmax. A lot of students will say, oh no, your Km is your 1/2 of the Vmax. But that doesn't make sense. Km is a concentration. Vmax, or velocity, it's a measurement of product, how much product you're forming per unit of time. So if you ever hear somebody say Km is equal to 1/2 of the Vmax, just shake your head in disappointment. That is not true. This is not true. This is equivalent to saying that a concentration is equal to that. No. Any mathematician would look at that little equation that I just made and and puke, okay? All right. Let's see. Okay, so we found our Km value, and the Km value is this number right here, which corresponds to this dot, which is 0.66. So your Km is 0.066 millimolar. And that is your substrate concentration at which your initial velocity is equal to 1/2 the Vmax. All right, let's proceed. Oh, here's something that I should mention. So the way that we're able to get this graph right here, this rectangular hyperbola, is by using the Michaelis-Menten equation, which is initial velocity is equal to Vmax times the substrate concentration over Km plus substrate concentration. So this equation, which I actually included over here, that'll be equation number 3. That is the equation which you can actually use to get every single one of these Michaelis-Menten graphs. And the reason for that is because this is a constant, Vmax is a constant, right? Because Vmax is equal to K2 times the amount of enzyme times the number of active sites. Every single one of these numbers right here is a constant. Unless you decide to add more enzyme, then it's not a constant. But you assume that the amount of enzyme is constant throughout the whole experiment. Okay, so Vmax is a constant, and so is Km. So what's the only thing that you can increase or decrease in these experiments, right? In these experiments where you have a beaker or some type of, solution holding device, and you add in enzyme. What else can you control? The amount of substrate, right? Because the enzyme reacts with the substrate, forms the enzyme substrate complex, and then forms enzyme plus product. So the amount of enzyme is constant, so therefore Vmax is constant. Km is also a constant, and as you increase the amount of substrate, your velocity increases until you reach Vmax. Alright. And that equation is, or the Michaelis-Menten equation, the velocity equation, is also right there. Although I will make one note to this equation. Here it says Ks. For the most part, it should be Km, because Km is not always equal to Ks. So they're not always equal, but sometimes they are. And we're going to go through an example where they are equal to each other. So I'm not saying this equation is wrong. I would never say that, okay? I'm just saying that it is more beneficial for you to use this equation when it has the Km value. If you use the Ks value, you might be a little disappointed if those two things aren't equal. That's all I'm saying, okay? So Ks is equal to K sub minus 1 over K1. So it's just like the Km equation, because the Km equation is K sub minus 1 plus K2 over K1. The only thing it's missing is the K2 value. So that's the only thing it's missing. Alright, so at this moment in time we have enough background information to be able to answer question number 5, which I conveniently skipped. So number 5, which of the following is false regarding Michaelis-Menten enzymes? So A, at low substrate concentrations, the enzymes follow first order kinetics. Is that true or false? That is true. What about B, at saturating substrate concentrations? What does saturating substrate concentrations mean? It means that you have a lot more substrate than you do enzyme. So we can write this as substrate concentration is much greater than enzyme concentration, which is what we have here in this example. The amount of substrate, which is those red dots, is greatly outnumbering the amount of enzyme that you have in that beaker. So at saturating substrate concentrations, the enzymes follow first order kinetics. Is that true or false? That is true. Follow zero order kinetics, yeah. That is true, right? Because as you increase the amount of substrate, the velocity isn't increasing because it's already reached Vmax. If you're at saturating substrate concentrations, you are at Vmax, okay? So if you are at saturating substrate concentrations, you are at Vmax. I repeat these things because I think they're important for you to know. So B is also true. So what about C? The enzymes consist of multiple binding sites and catalytic sites? That's a little questionable. And what about D? The enzymes display hyperbolic curves. Is that true or false? Do Michaelis-Menten enzymes display hyperbolic curves? The answer is yes. they do. And what about C? So I know we said that one was a little questionable, and the reason why I put a little squiggly line next to it is because it could seem wrong just because it doesn't say that they could consist of multiple binding sites and catalytic sites. But let's see, if I change it, and I'm not changing it because it's more convenient for me. I'm changing it because that's really what I meant. The enzymes could consist of multiple binding sites and catalytic sites. For Michaelis-Menten enzymes, that is definitely true. And we covered that at the very beginning. Michaelis-Menten enzymes have one catalytic subunit, but they can have more than one active site. More than one active site, a catalytic site. And now if this right here would have said multiple subunits, it would have definitely been wrong. But because they can or they could consist of multiple binding sites and multiple catalytic sites, that one is also true. Therefore, the answer is F. Okay. All right, so all those fancy new equations that we have, we're going to use them to solve these next few problems. So, number 6, a newly discovered enzyme was found to follow Michaelis-Menten kinetics. Further analysis of the enzyme has produced the following equilibrium constants: K1, K sub minus 1, K2, also known as the turnover number. So K2 is equal to K cat almost always for you guys, which is equal to the turnover number. All right. At what substrate concentration will the initial velocity equal 1/2 of the Vmax? So what did I tell you? That when the substrate concentration is equal to the Km value, your initial velocity will be 1/2 of the Vmax. So before we can answer this question, let's find the Km. So Km is equal to K sub minus 1 plus K2 over K1. And so Km is 6.5, whoa, that's wrong. So Km is 4.5 times 10 to the 5th inverse seconds plus K2, which is 3.7 times 10 to the 2nd inverse seconds, over K1, which is 6.5 times 10 to the 8th inverse smaller inverse seconds. Where is my calculator? There it is. Okay, so that is 4.5 times 10 to the 5th plus 3.7 times 10 to the 2nd over 6.5 times 10 to the 8th. All right, and the number that you should get is Km is equal to 6.93 times 10 to the negative 4th, and the units are molar, right? Because Km is a concentration. So this is your Michaelis-Menten constant. This is the affinity of the enzyme for the substrate, okay? So Km is a measure of affinity. It's not just a substrate concentration, it's also a measure of affinity. And we'll go through that in just a little bit. So this is our Km value, and we know that that Km is equal to the substrate concentration at which your initial velocity is 1/2 of the Vmax. So it's only when the substrate concentration is equal to Km. And we can prove that using this equation, the Michaelis-Menten equation. All right, so remember that Km is a constant, all right? Km only has one value, but the substrate concentration can be almost any value. So here is a little Michaelis-Menten graph. So this right here is your Km. But your substrate concentration can be any one of these values right here. But when your substrate concentration is equal to your Km, your initial velocity is 1/2 of the Vmax. Let's prove that. So we're going to say Km is equal to substrate concentration, or substrate concentration is equal to Km. When the substrate concentration is equal to the Km, what will be our initial velocity? Initial velocity is equal to Vmax times, we'll say Km over Km plus Km. So all I did was I swapped out those numbers. So what this gives you is initial velocity is Vmax times Km over 2Km. Units cancel out. Initial velocity is Vmax over 2, which means initial velocity is equal to 1/2 of the Vmax. Okay, so remember, substrate concentration can be any value on this little Michaelis-Menten graph that I showed you, but it's only when the substrate concentration is equal to the Km, only in that condition, when those two things are equal, that your initial velocity will be 1/2 the Vmax. So the question was asking, at what substrate concentration will the initial velocity be 1/2 the Vmax? And the answer is 6.93 times 10 to the negative fourth, which means that the correct answer is A. All right, number 6A. Does this enzyme follow rapid equilibrium or steady state kinetics? Here's the easy way for you to know. I'm going to write it over here. If Ks is approximately equal to Km, then the enzyme follows rapid equilibrium. And if Ks does not equal or does not approximately equal Km, then it follows steady state. So all we got to do is calculate Ks and calculate Km, and we'll find that answer. So we know our Km is 6.93 times 10 to the negative fourth molar. That's our Km. Our Ks, that equation is over here. That one. So Ks is equal to 4.5 times 10 to the negative fifth inverse seconds over 6.5 times 10 to the eighth inverse molar inverse seconds. So what number do you get when you calculate Ks? I put a -5 right there, that should be a +5. So 4.5 times 10 to the fifth over 6.5 times 10 to the eighth. That number is 6.92 times 10 to the negative fourth molar. So this is our Ks and this is our Km. Are they approximately equal? The answer is yes, they are. 6.92 is approximately 6.93, all right? It's approximately equal. So for that reason, since Ks is approximately equal to Km, the enzyme follows rapid equilibrium. So the answer to 6A is no. It does not follow steady state. It follows rapid equilibrium. There you go. Just circle rapid equilibrium, and you got it. I forgot that it said rapid equilibrium there. Okay, number 7. Another Michaelis-Menten enzyme has been discovered. Kinetic analysis of the enzyme resulted in the following rate constants. So there's our rate constants. Which of the following is true? The enzyme follows steady state kinetics. I don't know about that. The enzyme reaches rapid equilibrium between the ES complex and E plus S. And the enzyme is allosterically modulated, or D, none of the above. Let's calculate Km first. That way we can find out whether or not it follows rapid equilibrium or steady state. So Km is equal to K sub minus 1, which is 7.8 times 10 to the third inverse seconds, plus the turnover number, which is 9.1 times 10 to the third, inverse seconds, over K1, which is 3.3 times 10 to the 7th, inverse molar, inverse seconds. So what number is that? 7.8 times 10 to the third plus 9.1 times 10 to the third over 3.3 times 10 to the 7th. That should give you 5.12 times 10 to the negative 4th inverse molar. So that's our Km. Let's calculate the Ks now. Ks is equal to 7.8 times 10 to the third inverse seconds over 3.3 times 10 to the 7th inverse molar inverse seconds. So when you divide those two numbers, you should get this 2.36 times 10 to the negative 4th molar. So are Ks and Km approximately equal? No, they are not. 5.12 and 2.36 are definitely not approximately equal. They're both in the 10 to the negative 4th region, but 2.36 is not approximately equal to 5.12. Okay, so this is how you find out if an enzyme follows steady state or rapid equilibrium kinetics. So because Ks does not equal Km, that means that your enzyme follows steady state kinetics. So the answer for number 7 is definitely A. What about B? The enzyme reaches rapid equilibrium between the enzyme substrate complex and the E plus S. So that means that if it reaches rapid equilibrium in this step. What B says is that it reaches rapid equilibrium in this step right here, which is not true. What rapid equilibrium means is that if you put the enzyme and the substrate together, that it'll be going back and forth between E plus S to ES, back and forth really fast, without really going to E plus P, without going to the enzyme and the product. But steady state means that it reaches the enzyme substrate complex and it steadily goes in this direction. That's steady state. And it also steadily goes in this direction. Steady state kinetics and rapid equilibrium, they're a little convoluted. So if you have any questions, please come to Peer Tutoring, the best tutoring center to get biochemistry help. Okay, so the answer for number 7 is A. For number 8, For an enzyme that obeys Michaelis-Menten kinetics, what will be the initial velocity if the substrate concentration is 3/5 of your Km? Let's find this out. So these are very close to what your these questions are very close to what your exam may look like. So let's pull out the Michaelis-Menten equation. And you're probably wondering, why am I even using this equation? I'm going to show you. So here what they're telling us is that the substrate concentration is 3/5 of the Km. We don't need anything else. So substrate concentration is equal to 3/5 of the Km. So since these two things are equal, I can plug in 3/5 of Km. Whoa. I can plug in 3/5 of the Km right wherever you see substrate concentration. So I'll plug that in right there. So the initial velocity is equal to 3/5 Km times Vmax over Km plus 3/5 Km. So what is this equal to? So initial velocity is 3/5 of the Km. I'm going to do this step by step because my math isn't the best. So then the next part will be 8/5 Km times Vmax at the top, I forgot. And then the 5's cancel out, and your initial velocity is 3/8 of the Vmax, which is one of the answer choices, so I'm very happy. Okay, don't you guys hate that? You know, whenever you calculate something and it's not one of the answer choices, it lets you know that your process is wrong. Okay, but that's our initial velocity. It's 3/8 of the Vmax. All right, for number 9, an enzyme that obeys Michaelis-Menten kinetics, what will be the initial velocity if the substrate concentration is equal to the Km? So when the substrate concentration is equal to the Km, remember Km is a constant, so whenever the substrate concentration is equal to your Km, we're going to solve this just like the one before, even though you've already seen the work. So because these two things are equal for this problem, I can plug in S for Km. So I'm going to plug that in right there. And the other one I did it with Km. Here I'm going to do it with S. But it still works out the same way. Your initial velocity will be Vmax times S over 2S. Substrate concentration cancels out. Your initial velocity is Vmax over 2. Another way of saying it is equal to 1/2 Vmax. So for an enzyme that obeys Michaelis-Menten enzyme kinetics, what will be the initial velocity if substrate concentration is equal to Km? The answer is A, 1/2 of the Vmax. For another enzyme that obeys Michaelis-Menten kinetics, what will be the Vmax value in moles per minute if the initial velocity equals 50 moles per minute when the substrate concentration is 0.5 of the Km? Okay, I forgot how to do this one, but I'm sure that we can figure it out together. I didn't calculate any of these beforehand, but if you know the process, to be true, then you cannot go wrong. So whatever the answer is, I'm sure it's going to be the right one. Okay, so what is the Vmax value? So Vmax is what we want, and we're given the initial velocity. So I'm going to assume that this is the right equation that we can use. We're given that, and we also know substrate concentration and the Km. So we know this, we know that, and that. We're in good shape. Wait, no. We don't know Vmax, but we do know this. I got a little excited. But here. Boom. We know everything but Vmax, because that's what the question wants. Alright, so let's plug that stuff in. So this is the initial velocity right here, 50 moles per minute. So 50 moles per minute. This is equal to Vmax times the substrate concentration. The substrate concentration is 0.5 km, so I'm going to substitute 0.5 km. And then at the bottom we still have km plus 0.5 km. And what does this look like? So 50 moles per minute is equal to Vmax times 0.5 km over 1.5 km. Km cancels out, so then you have 50 moles per minute is equal to Vmax, and then you have 0.5 over 1.5. I'm just going to write it like this. 1.5, that's 3 over 2. Just because it's a lot easier for me to divide fractions than it is to divide decimals. Or you know what? I just realized I could have done it that way. Hey, you know what? I told you, okay? Math, not my strong suit. Alright, so then the 2's cancel out, and then you have 50 moles per minute is equal to 1/3 of the Vmax. And so then, since we want Vmax, we must isolate it, and that means multiplying both sides of this algebraic expression by 3. So Vmax is equal to 150 moles per minute. It's one of the answer choices. So it's the right answer. I promise. Yes. Okay. So the way that I could have done it over here, which is embarrassing, but you know, I am not above making mistakes. I make mistakes all the time. All right, so that's 1.5. Yeah. So I could have just divided this and this by 0.5. And then this would be, how many times is 0.5 going to 1.5? That's 3. How many times is 0.5 going to 0.5? That is 1, 1/3. Okay. Let's see. Number 11. From the previous question, what will be the initial velocity if the substrate concentration is equal to your Km? Okay, we know the Vmax. That's 150 moles per minute. When the substrate concentration is equal to the Km, what is it? When the substrate concentration is equal to your Km, your initial velocity is 1/2 of the Vmax. So question number 11 follows from question number 10, and we know the Vmax to be 150 moles per minute. So therefore, if your substrate concentration is equal to your Km, remember Km is a constant, substrate concentration can be any value, but when it's equal to the Km, your initial velocity is 1/2 of the Vmax. Your Vmax is 150, therefore the answer for number 11 is, what's 150 divided by 2? Good job, 75. There you go. So for number 11, the answer is A.